It's Valentina Betancourt, and this is my presentation for Lab 5, Faraday's Law. First, an introduction to the lab. The purpose of this lab was to collect data of a falling magnet through an aluminum tube, and to model the magnet and the tube's interaction computationally using GlowScript. We then compare the model with the theoretical data. In terms of Faraday's Law, in this lab we experience a current that produces a magnetic field, which then exerts a force on the source of an external magnetic field. In our lab, this will be our falling bar magnet, and the induced current is driven in a tube of aluminum foil. Some of the physical principles that we will be observing and using in this lab. First is Faraday's Law, once again, which will help us to calculate the current induced in each ring. Then the Biot-Savart Law, which will help us to calculate the force exerted on each current-carrying ring by the falling magnet. And lastly, Newton's third law, which states that for every action there is an equal and opposite reaction. We will use this to calculate the force exerted in the falling magnet by the whole tube of current-carrying ring. The first thing I did upon completing my lab was to calculate the average time it takes the magnet to fall through the tube. Since I carried the experiment out 5 times, I measured the time 5 times and took the average of these and arrived at 0.55 seconds. Some of the observations that I made was that as the magnet falls down, it is attracted to the aluminum wrapped around the tube, and therefore it falls more slowly. Essentially, we can state that if it were falling through free space, it would take less time than it did when falling through the aluminum-wrapped tube. Here I have some of the initial data and some of the measurements for my tube. First, we must state that the bar magnet in this experiment is modeled as a point charge. And in terms of the tube and the dimensions, the length that I measured was 0.32 meters, the radius was 0.012 meters, and the thickness was 0.01 meters. In terms of the magnetic moment, this was computed in Lab 3 and used for this lab, and my value for mu was 1.72. First, I'd like to go over some of the concluding questions that were raised at the end of the lab before going in depth about my computational model. First, why can't we use a ferrous tube instead of an aluminum tube? This is simply because the magnet would be attracted to the ferrous tube, and this would inhibit in our experiment, and therefore it is better to use the aluminum tube. What if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? I stated that the falling magnet would fall more slowly than it did. This can be explained with Ohm's law, as low resistivity would mean greater induced current and therefore a more slowly falling magnet. Next, what if holes or slots were cut into the tube? How would this affect the ring currents in our model? I stated that the falling magnet would fall faster in this case. This is because cutting holes would reduce the magnetic force from the rings, and therefore there would be less induced magnetic fields. How does the total time in the tube of our real-world system compare to the computational system, and how could we make the computational system more accurate? First, the time in my computational model was less than in my real-world system. In the real world, I measured about 0.55 seconds, while in my simulation it was around 0.3 seconds. This could be due to the value of the calculated magnetic dipole moment mu. I realized that when I attempted slightly different values for my mu, the higher the value, I achieved results that were closer to the 0.55 seconds that I observed in real life. And some of the ways that we could make the computational model more accurate is first that it doesn't account for air resistance, and this air resistance slows down our magnet. If we accounted for this, we could achieve results that were more similar to the real-world system. And another suggestion is that we could use more rings. This could help us to analyze the magnet at more points throughout its fall. The next question states that the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate the current flowing in opposite directions, and which color corresponds to the clockwise current and which to the counterclockwise, and how can we know? As the magnet falls, we see that there are red rings around the bottom part, and since it's obviously falling downwards, the increasing change in flux is also downwards, and therefore the induced current is flowing counterclockwise. Therefore, we can state that red is counterclockwise and blue is clockwise. Lastly, what happens to the dynamics of the system when you flip the magnet around? I stated that there was no significant change since there was no change in the observed time. Next, I have a couple of snapshots of my code and the individual measurements that I input into it. In the first arrow, we simply input the values for the geometry of the tube, such as its width and its radius. Next, in the next arrow, we can see the properties of the magnet and where we insert the value for our mu, in my case 1.72. Lastly, we visualize the bar magnet where we create the cylinder itself. Here in the first arrow, we can see the calculation for the gravitational force on the magnet, and the calculation for the magnetic force from the tube on the magnet in the first arrow. In the second arrow, I'm highlighting the calculation for the magnetic force on the magnet, the net force on the magnet, and lastly, we update the magnet's velocity as well as its position. Here I have a snapshot of the output of my code. On the left-hand side, we're simply visualizing the tube. This is once the magnet has completely fallen. And on the right-hand side, I have a graph for velocity versus time. One observation that I made is that there was a slower velocity from time t equals 0 to 0.05 seconds, which we can see with the first blue arrow. And then the velocity increased from time t equals 0.05 seconds to 0.3 seconds when it had completely fallen. And in order to conclude, I just wanted to state that the real-life simulation found the time in the model, time in the tube to be around 0.55 seconds, which was much more than the computational model. And although this was quite a significant change, I think that it could most likely be due to the value of the magnet's magnetic dipole moment, mu. Thank you so much.